Build better and save with modern timber bridges. This was the theme of a nationwide timber bridge conference held in May 1987 at University Park, Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. Closing comments for the Timber Bridge Conference were presented by Dr. John B. Christ from the USDA Forest Service.
As closing comments for this conference, I am not going to try to recap all of the speakers that you have heard because they are experts in their own right in their individual fields. However, we would like to remind you of some of the reasons of why we have this conference and a few messages that we hope that you take home with you. The overall purpose of this conference and why it was convened in the first part was a recognition that within the United States, and also particularly in Pennsylvania, we have some real transportation needs from the standpoint that there are many deficient bridges out there. We also have an excess timber resource that is growing in abundance and that the species available are definitely suitable for timber bridges. And the third is we would like to create jobs through the stimulation of the forest products industry and local contractors. We thought that timber bridges are an ideal way to affect all of these above things. The conference was convened to call attention to the attributes of timber and timber designs while also giving caution as to limitations on how to cope with any limitations that are inherent with wood. One of our real problems is that most engineers are not trained in the use of wood. In their education experience, they are trained in steel and concrete, but are very limited in their training with wood. Also, municipal managers usually don't consider wood as an alternative to steel and concrete in the construction of bridges. The advantages of treated timber are many, and when they're used for bridges, there may be some real cost advantages, as many speakers have alluded to here today. Also, aesthetics is a very big one. When you have a state such as Pennsylvania, in which recreation and the aesthetics of the countryside are important, timber bridges fit in very nicely. We also know that timber is not affected by road salts. Therefore, they are very long-lived and need less maintenance throughout their lifetime than those constructed of steel and concrete. We also know that the preservative treatments that we use to get this long life are functionally sound and very environmentally safe, as proven over and over again. Another nice advantage of timber in the design of bridges is the flexibility. We can make all kinds of sizes and shape. We are not limited in either length or weight capacity, as most people sometimes have the conception. And also, they can be used in conjunction with other materials. We can make all wood bridges where the cribs, abutments, and pilings and whatnot are also timber, but we can also use them with steel and concrete, concrete for the abutment, steel for the stringers, so the flexibility of design is very, very great. Wood is a wonderful material. Its extraordinary strength to weight ratio allows for many designs that may not be possible with other materials. It's easy to work and to machine and shape. It also has very strong shock resistance and impact loading. However, it's not without limitations. Water is its enemy because excess water causes an environment for decay pathogens. And also in design, strength is not a problem, but deflection may be, because deflection in wood is greater than in steel and concrete, so therefore that must be considered in any design. You have been cautioned throughout the conference that if you use timber to do it right, use properly treated timber, make sure that any cuts during fabrication or erection are treated, and that the hardware is galvanized or epoxy coated. Use design values Here is probably the biggest limitation in our knowledge. The forest products industry has not done as good a job as the steel and concrete industry in packaging its information. We are more fragmented, and we have not had as strong a trade organization and lobbying efforts. However, some of those design values are out there, and they can be used. It's just an added hurdle, but it is certainly not a total obstacle. So there's a real opportunity out there. There is a resource that needs used. There is a need for additional transportation, and we, as promoters of wood, designers of wood, and fabricators of wood, should seize this opportunity and go out and make the most of it.
Build better and save with modern timber bridges. This was the theme of a nationwide timber bridge conference held in May 1987 at University Park, Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. Closing comments for the Timber Bridge Conference were presented by Dr. John B. Christ from the USDA Forest Service.
As closing comments for this conference, I am not going to try to recap all of the speakers that you have heard because they are experts in their own right in their individual fields. However, we would like to remind you of some of the reasons of why we have this conference and a few messages that we hope that you take home with you. The overall purpose of this conference and why it was convened in the first part was a recognition that within the United States, and also particularly in Pennsylvania, we have some real transportation needs from the standpoint that there are many deficient bridges out there. We also have an excess timber resource that is growing in abundance, and that the species available are definitely suitable for timber bridges. And the third is we would like to create jobs through the stimulation of the forest products industry and local contractors. We thought that timber bridges are an ideal way to affect all of these above things. The conference was convened to call attention to the attributes of timber and timber designs, while also giving caution as to limitations on how to cope with any limitations that are inherent with wood. One of our real problems is that most engineers are not trained in the use of wood. In their education experience, they are trained in steel and concrete, but are very limited in their training with wood. Also, municipal managers usually don't consider wood as an alternative to steel and concrete in the construction of bridges. The advantages of treated timber are many, and when they're used for bridges, there may be some real cost advantages, as many speakers have alluded to here today. Also, aesthetics is a very big one. When you have a state such as Pennsylvania, in which recreation and the aesthetics of the countryside are important, timber bridges fit in very nicely. We also know that timber is not affected by road salts. Therefore, they are very long-lived and need less maintenance throughout their lifetime than those constructed of steel and concrete. We also know that the preservative treatments that we use to get this long life are functionally sound and very environmentally safe, as proven over and over again. Another nice advantage of timber in the design of bridges is the flexibility. We can make all kinds of sizes and shape. We are not limited in either length or weight capacity, as most people sometimes have the conception. And also, they can be used in conjunction with other materials. We can make all wood bridges where the cribs, abutments, and pilings and whatnot are also timber, but we can also use them with steel and concrete, concrete for the abutment, steel for the stringers, so the flexibility of design is very, very great. Wood is a wonderful material. Its extraordinary strength to weight ratio allows for many designs that may not be possible with other materials. It's easy to work and to machine and shape. It also has very strong shock resistance and impact loading. However, it's not without limitations. Water is its enemy because excess water causes an environment for decay pathogens. So, and also in design, strength is not a problem, but deflection may be. Because deflection in wood is greater than in steel and concrete, so therefore that must be considered in any design. You have been cautioned throughout the conference that if you use timber to do it right, use properly treated timber, make sure that any cuts during fabrication or erection are treated, and that the hardware is galvanized or epoxy coated. Use design values. Here is probably the biggest limitation in our knowledge. The forest products industry has not done as good a job as the steel and concrete industry in packaging its information. We are more fragmented, and we have not had as strong a trade organization and lobbying efforts. However, some of those design values are out there, and they can be used. It's just an added hurdle, but it is certainly not a total obstacle. So there's a real opportunity out there. There is a resource that needs used. There is a need for additional transportation, and we, as promoters of wood, designers of wood, and fabricators of wood, should seize this opportunity and go out and make the most of it.
Bridges. No bridge opening would be complete without the cutting of the ribbon. But before those scissors close, it might be well to recall just what occurred.
Very much. I appreciate the opportunity to come here and come back to my alma mater and spend a few pleasant hours with all of you. I also want to welcome those of you who are attending this conference from outside of the state. Welcome to Pennsylvania. Welcome to this great commonwealth of innovation and new direction. We are busily about the business of establishing a partnership in Pennsylvania for economic development. That partnership is bringing together minds and energies and talents from the public and the private sector in the interest of creating new jobs and new opportunities in Pennsylvania. Part of the mission of that partnership is to develop new opportunities, new and creative thinking that relate to potential job creation. The reason I'm here today is to bring you greetings from Governor Casey and to commit to you that we are willing to work with you on innovative approaches and innovative ideas. For example, we have a vast reserve of hardwoods in Pennsylvania. Pennsylvania is, in fact, named after our beautiful sylvan settings in many parts of the state. Indeed, this was known as Penn's Woods early on under the founding guidance of William Penn. We have never fully developed our resources in that regard, and there is every reason to believe that our timber industry in this state could be developed and be the source of hundreds and maybe thousands of new job opportunities. It is a prospect that is at least worth exploring. The bridge that we are standing on here is ample evidence that there could be new and exciting uses for our hardwoods in Pennsylvania. And we feel very excited about the opportunity of demonstrating some of those uses. I know that you have a very rigorous two-day conference and you're learning all of the aspects of the construction and the engineering that go into this bridge, and I'm certainly not an expert on those aspects. But I do know this, that we have a newly energized Department of Transportation in Pennsylvania. We have a newly created, enthusiastic economic development partnership. We have a Department of Environmental Resources that's willing to work with us. And when you put all of those ingredients together with the talent of private entrepreneurs and people who are willing to help us move ahead, good things like creative design and construction of bridges start to happen. I commend all of you for your attendance at this conference. We commit very strongly all of our resources to being creative and providing new jobs and opportunities for our citizens. With that, I thank you for allowing me to join you, and I'll turn the program back over to our MC. Thank you very much. 1, 2, 3. Yay!
Since this bridge is the focal point not only of the conference, but of a great deal of interest by federal, state, and municipal officials, a research program was begun to evaluate the tensioning technique used in the design of this bridge. The purpose of this research effort is to determine the forces in the transverse post-tensioning rods over a period of time. The action force will be measured with load cells, which have been placed on 3 of the steel bars. The 3 bars selected were located near the support, quarter point, and midspan of the bridge. It is felt that the force in these bars is representative of the force in all of the transverse bars on the bridge. Measurements will also be taken for moisture content and camber, or the deflection of the bridge. Moisture content directly affects the force in the bars because of shrinkage and swelling. The tests are being taken on a weekly basis, and a research report will be issued by the Pennsylvania Department of Transportation. This was the theme of a nationwide timber bridge conference held in May 1987 at University Park, Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. Sawn, microlam, and truss bridges was addressed by Paul Nicholas from Truss Joist Corporation.
The subject of my presentation will be on sawn, truss, and microlam timber bridges. I will begin by talking about log stringer bridges as one of the oldest types of timber bridge construction, then talk about covered bridges, and then give several examples of how sawn timbers have been used in the construction of bridges over the years. I will then talk about the research in the 1960s by the Forest Products Laboratory on the development of press lam for use in timber bridges. This will lead me into the discussion of the use of microlam, laminated veneer lumber, a product of my company, Truss Joist Corporation, and its potential use in the fabrication of timber bridges. One of the primary advantages of microlam is that it is easily treated with preservatives to protect it from decay. The other advantage, of course, is its high reliability and its availability in long lengths. Currently, our company is looking into the potential for use of microlam in the pre-stressed type decks that have been discussed during this seminar, and I'll give some information on the manufacture and design use of microlam laminated veneer lumber. In conclusion, I want to point out the primary advantages of using microlam in timber bridges are that it is highly treatable with preservatives, it's available in long lengths, and it is a highly reliable structural timber product.
Well, good afternoon. I'm Bruce Pooley with the American Institute of Timber Construction, and I'm here primarily today to talk to you about glue laminated timber used in timber bridges. First of all, I'd just like to give a little background. AITC is a national trade association. They represent manufacturers of glue laminated timber throughout the nation. Our primary goals are to promote the use of wood glue lam throughout the country, provide quality control inspection services, and also to develop standards and codes for use in the building industry. If you're familiar with glue lam, you may know that we basically take individual pieces of sawn lumber, fabricate those, and use adhesives to form large timbers of any size, depth, or length that may be required for a job. Typically, the species that are used are Douglas fir and southern pine. Those are the two primary species that are used. We do have standards that allow for other species to be used. The adhesives you might be interested in are typically a wet use adhesive, phenyl resorcinol and melamine urea are the various adhesives that are commonly used in our production. With this laminating of the timber, we get a laminating effect, which in other words gives us increased strength capabilities due to the separation of other characteristics of the tree, which tend to reduce the strength somewhat. This laminating effect tends to disperse those characteristics and provides us with higher strength. Also, the large timbers, as sawn timbers, would require quite a lengthy seasoning period, whereas with smaller timbers, say 2x6s, we're able to dry the individual pieces down to a lower moisture content. Thus, the overall moisture content of the glulam is significantly lower, and as we know, the strength increases when we have lower moisture content. So those are a couple of benefits that we see from the laminating effect, which is briefly an overview of glue laminated timber. Now, specifically, I would like to talk about the several types of timber bridges, or the types of timber bridges that are available using glulam components. Basically, we have two different systems that are used most of the time. Glulam stringers, often referred to as a girder type bridge also. The main bending members span longitudinally from abutment to abutment. These stringers are typically based 5 or 6 feet on centers, depending on the load situation, the other physical dimensions of the bridge. Another very common and somewhat new is the longitudinal bridge system, where the actual laminated deck panels themselves are carrying the entire load. In other words, there's no girders or stringers involved. The deck panel acts as the bending member across the span. Now, just getting back to the stringer type bridges, here we have provided stringers, but we do need the surface to carry the loads. We have two types that are normally used. We have a transverse glue laminated deck, which uses a dowel between the deck panels to help transfer loads. And we also have the glue laminated deck without the dowel system, which does not transfer loads between the panels. Now, with these two types of systems, there's some advantages and disadvantages to both of them. Presently, we feel that the system, so-called non-dowel system, is probably a more economical and easier to install type of deck system. Typically, these decks, whether they be doweled or non-doweled, are anywhere from 5 1/8 inches deep to 8 3/4 inches deep. The width of these panels is typically 4 feet, 48 inches, and the length of them for the transverse application would be whatever the roadway width required for the bridge is. So that gives us a background on the girder stringer bridge, along with the various types of deck. Now, a few more comments. Normally, these bridges can range anywhere from a 20-foot span all the way up to approximately 80-foot span and be in an economical range. The roadway widths vary anywhere from our minimums. We show about a 24-foot wide bridge up to about 36 feet, are generally the most economical ranges that we have there. Now, longitudinal bridges, where, as I mentioned earlier, the decking acts as the carrying member. The spans for a longitudinal deck bridge generally range from about 8 feet up to 30 feet. The thicknesses of these decks, of course, will vary considerably depending on the load in the span. Normally, the 6 3/4 inch deck all the way up to a 14 1/4 inch deck can be manufactured and supplied for this situation. A question that may come into your minds is the typical loads that are used. Presently, AITC is developing a manual that will come up with typical bridge sizes for loadings in accordance with AASHTO, the HS-15 and the HS-20 loadings. There have been numerous bridges installed in the field according to these specifications, and they seem to work quite well. So that basically tells you of those types of bridges. There is one other type of bridge that has seen some use recently. We do have the superstructure consisting of radial arches along with horizontal beams and also the laminated deck. These are very popular in some of the more mountainous regions where the aesthetics of the bridge enter into it, and where you may have to provide a bridge with significant headroom between the waters and the bottom of the deck of the bridge. Okay. Now, with the basic designs and loading applications, as I mentioned, the specifications that we're presently developing are in accordance with the AASHTO specification. Typically, the girder bridges, we're looking at the specific bending, horizontal shear, and even the deflection of those members as controlling factors of the bridge. In AASHTO, they have provided the maximum live load moments. Then you would calculate your dead load moments due to the weight of the structure, etc., and determine your bending requirements and calculate the cross-sectional requirements, section modulus values, if you would, for the bending. Also, the horizontal shear, again, the procedure is shown in the AASHTO manual. Presently, we do follow those requirements, although technically we are looking at some modifications for determining these shear values. A lot of the load distribution has been reviewed recently in research at Iowa State University, and we have found that there are some distributions that load distributions that have significantly shown that we can decrease the actual load in the calculations for those distributions. Deflection, currently we are using a distributed live load in the deflection calculations. Our limiting deflection right now is the span over 300. This is a policy that's been developed at AITC. So that pretty much takes care of the design portion of it. Just a couple other comments briefly. Of course, we require that the bridges be made of preservatively treated materials. Commonly the creosote and the pentachlorophenol treatments are used. We note that normally with the bridge deck systems that the decking acts as a bridge over the stringers. Therefore, we can use dry use stress values. We don't have to use wet use stresses. Another important consideration is the placement of a wearing surface along the deck. Typically, a asphaltic bituminous wearing surface is used. And then, of course, we have some very specific rail designs which are used in accordance with the AASHTO specifications. Now, a lot of this information on the design is included in the AITC Timber Construction Manual, 1985 edition, which was printed in 1986 and is currently available. One other subject that I would like to touch on just briefly would be in the rehabilitation of bridges. Glued laminated deck panels are used quite frequently to replace deteriorated concrete panels over steel stringers. The installation is quite easy and many times very economical. Some of the other benefits are that the deck itself does not deteriorate under the application of de-icing salts, as is common for concrete, and has a large effect on the steel also. So this is one area where the glued laminated timber decks are also entering into, is the rehabilitation of existing bridges. In summary then, we've touched basically on the laminating, the use of glue laminated timber decks, and the various types of glue-lam decks that are commercially available today. That is a girder system with transverse decks using either a dowel or non-doweled system. We also have longitudinal decks, and we also have a system that includes the use of radial arches along with transverse decks. On behalf of AITC, I'd like to thank you for this opportunity to speak to you today. Thank you very much.
Build better and save with modern timber bridges. This was the theme of a nationwide timber bridge conference held in May 1987 at University Park, Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. The subject of environmental and aesthetic considerations for modern timber bridges was discussed by David A. Webb from Koppers Company.
I'm here today to discuss wood preservatives, their environmental and aesthetic considerations as used in timber bridges. Over the years, there's been some concern with regard to environmental concerns and the use of preservatives and preservative-treated products in the environment. I think first we need to just briefly give a short description concerning what are wood preservatives and what are their potential uses in the marketplace, how they can best be used for their best benefit as preservative systems. Wood is a natural material. It's a material which can have increased performance when wood preservatives are used. Naturally durable woods are no longer readily available. These woods are species such as walnut, honey locust, black locust. Redwood in particular is a wood which does not have the same characteristics which it used to have as a virgin timber. The second growth redwood material is not nearly as durable as it once was. We believe that wood preservatives have a very excellent possibility of servicing and have, from their reputation over the years, given excellent service life performance when applied to non-durable timbers. Woods such as softwoods, pines, Douglas fir, and then the hardwood timbers such as white oak, the oaks, maples, etc. Society today has a concern for pesticide and insecticide materials that are used in the environment which may have an effect on man or the environment. They believe that there are unknown areas. They are searching for information. And essentially, the federal government established the Environmental Protection Agency with the thought that this agency would look into a number of the areas that are of society's concern. The RPAR process, which is the rebuttable presumption against re-registration, focuses specifically on insecticide and pesticide-type products and what their effects are in the environment and also on man. What are the risks and the benefits of these products, and do the products' benefits outweigh the potential risks? The RPAR process is a procedure whereby EPA looks at and asks the registrants of various pesticide materials to come forward and explain the benefits versus the risks. The RPAR for the three major wood preservatives, creosote, pentachlorophenol, and the waterborne arsenicals, was initiated in the 1970s. In October of 1978, position document number 1 was first issued by the EPA. The industry in turn responded with a rebuttal explaining our position with regard to the uses and the benefits, and also data which would focus on the concerns that EPA had concerning these materials. Subsequently, in January of 1981, position document 2.3 was issued, which were proposed regulatory actions. These actions would be placed on labels of pesticide products, specifically on the 3 products of creosote, pentachlorophenol, and the waterborne arsenicals. Again, the industry answered with the rebuttal to position document 2.3, and once again in July of 1984, EPA issued position document number 4, which was the final regulatory action concerning labels, restricted use of the pesticides, and again, the 3 specific pesticides, creosote, pentachlorophenol, and the waterborne arsenicals. I believe it is significant to note that EPA's final deliberations indicated that the benefits far outweighed the risks of these preservatives. The preservatives were continued allowed for use. They would have some restricted use applications and could only be used by those operators who were certified to use the products. Also, as a conclusion to the RPAR process, the industry voluntarily came forward with a consumer awareness program and subsequently published consumer information sheets. There's information in the consumer information sheets which focuses on the use handling characteristics of pressure-treated wood. And of course, this is a very important area which those people who are handling pressure-treated wood need to be aware of the kinds of potential hazards that may occur, although they are very minimal. Which leads me also to another area which we need to discuss, and that is the potential exposure hazards of individuals to pressure-treated wood. This hazard is extremely minimal. There's been a number of tests conducted by both the industry and by the various government agencies which indicates that there is no hazard. It's more or less a housekeeping procedure. Good personal hygiene practices need to be followed. You wear goggles, you wear gloves, long sleeve shirts. Just make sure that minimal contact, just as would normally occur when you were sawing or handling a piece of untreated wood. Pressure-treated wood, woods that are treated with creosote, pentachlorophenol, or waterborne arsenicals can be handled in the same manner as an untreated piece of wood. I should also like to point out that during the RPAR process, the industry conducted a number of different studies. Fate of preservatives in the environment, both air, water, and soil studies. There were some independent studies conducted at Mississippi State, Also some additional air monitoring studies at a number of different plants, some water studies conducted by various representatives in the industry. And in every case, none of the limits which are set by the federal government were exceeded. A number of the materials, a couple of the wood preservatives, pentachlorophenol and creosote, are readily biodegraded within the environment. The copper chrome arsenic, which is present in waterborne arsenicals, the CCA material, do not accumulate to any significant amount and do not present any adverse situations as far as individuals or the environment are concerned. In conclusion, I'd like to briefly summarize that wood preservatives, basically all three of them, creosote, pentachlorophenol, and the waterborne arsenicals, are products which have extreme benefits and are very useful in our society today. They increase the service life of non-durable timbers. They also conserve a very vital natural resource, and that's timber, our forests. These benefits outweigh any potential risk which may occur in using wood preservatives, and the exposure of man or the environment to these products do not present any significant risk.
The objective of wood preservation is simple, and that is to deny the decay organisms their food source. You could also attempt to deny them an adequate supply of air, moisture required for their environment, or the temperature range which they need. However, the easiest thing to do is to deny them the use of wood as a food source. And in the mid to late 1800s, the Europeans began to develop modern wood preservation methods. Up until that time, surface applications of various animal, mineral, and vegetable oils had been tried. But with the European developments of pressure treating and a variety of chemicals applied through pressure, vacuum, and heat, we began to develop today's pressure treating methods. And over the years, a variety of chemicals and processes have been tried, so that now we have some rather specific processes and chemicals for the specific end use of the wood product. Today, the principal chemicals available are creosote, pentachlorophenol, and the inorganic arsenicals, often referred to as CCA, chromated copper arsenate, or ACZA, ammoniated copper zinc arsenate. As a user of pressure-treated wood, you're not affected by the application of the regulations at the plant. You will receive, with each order of pressure-treated wood, a consumer information sheet looking somewhat along this line, which the wood preserving industry developed in cooperation with the Environmental Protection Agency. This sheet will have on it some common sense directions for the use, handling, and disposal of pressure-treated wood. You also need to be aware that there is no EPA-imposed limitation on the use of pressure-treated wood for bridges. While treated wood is not to be used in direct contact with human drinking water, there is a specific exemption for, quote, incidental contact such as docks and bridges, end quote. Now, the consumer information sheets also recommend that you dispose of any scraps or pieces of pressure-treated wood in a landfill or in your municipal trash disposal process. It is not recommended that you burn these scraps in your backyard barbecue or in the job site or any other place, but that you dispose of them properly, and that is in the landfill or in your municipal trash collection. Again, pressure-treated wood can be used for docks and bridges. There is no limitation on that use. And that applies to all three of the preservatives. Now, treated wood is available to you as bridge builders or other construction of wood products. Right now, about 40% of the southern pine lumber that's produced annually is pressure-treated. And over the years, there's been an increase in the volume of all woods that have been pressure treated, going from about 327 million cubic feet in 1978, 349 in 1981, up to 519 million cubic feet in 1985. The bulk of this material has been pressure treated with one of those arsenical compounds, 60%, and that was used for lumber, poles, timber, piling. Creosote accounted for 25% of that volume, principally in railroad ties, poles, piling, and bits of lumber and timber. Pentachlorophenol, used principally for utility poles, accounted for 10% of the production in 1985. Other chemicals took care of the remaining 5% of the chemical use. There are a lot of plants around the country which produce pressure-treated wood. There are 560 plants in 1985, and based on our knowledge of new plants coming online, there should be about 570 plants show up in the 1986 survey. 14 of those pressure treating plants are in Pennsylvania. Now, the bulk of the lumber and timber piling easily available to you as a bridge builder today would be softwood, particularly southern pine and Douglas fir. Most of the Pennsylvania and other hardwoods that are treated today are usually used for railroad ties, switch ties, and for railroad bridges. There is no technical reason why more Pennsylvania wood could not be used for the cribbing, stringers, and decking of timber bridges. However, that which is available to you today is primarily the softwoods. Looking at the relative treatability of Pennsylvania woods, we find some which are easily treated and some which are very difficult to treat. Now, the sapwood of most species is fairly easy to treat, and most of it can be rather uniformly treated. There are some exceptions to that, which you'll want to check out in your local tables of wood treatability. Treatability can be increased by steaming the wood prior to treatment or incising in some cases. Incising is putting small knife cuts in the surface which help speed the flow of the chemical into the wood. Wood is generally classified as to the relative ease of the heartwood. That's the center or the more dense portion of the tree to be treated. As far as Pennsylvania species go, the easy to treat heartwood portion of the tree are in the ash, the elm, and the red oaks. Not the white oak, but in the red oaks. Moderately difficult species to treat are the eastern white pine, hickory, and maples. The ones which are difficult to treat are hemlock, poplar, sycamore. Very difficult, we get to the beech and white oak. Now, difficult doesn't mean impossible. It requires some skill on the part of the wood preserver to get the chemicals into the wood, the proper depth of penetration, and to retain the proper amount of chemical in the wood for service. In specifying pressure-treated wood, you ought to rely on the standards of the American Wood Preservers Association. That's a professional body formed in 1904, designed to develop the standards, the treating specifications for pressure-treated wood. And there are separate standards, both for the chemicals that go into the wood and the processes, as well as the depth of penetration and the amount of chemical to be retained in the pressure-treated wood. So refer to those specifications, make sure your supplier knows what it is you want. To further assure quality, you ought to be requiring grade-marked lumber and timbers going into the pressure treating process, and you can check with any of the American Lumber Standards Committee's approved grading agencies to find out their standards for wood lumber going into the pressure treating process. And you should also specify a treating quality control group, such as the American Wood Preservers Bureau or any of the other similar groups, to assure that you are getting the pressure-treated product that you need. Specify the product you want. Usually you should require that it be dried subsequent to treatment, or at least surface dried. Now, in Pennsylvania, your timbers could be used as the single pieces in the bridge. They could be laminated with other pieces to make larger members, or they could be used as part of stress panels. Part of the current difficulty is the lack of stress tables for Pennsylvania hardwoods, which makes it a bit difficult to specify and know exactly what their performance will be in a bridge or other structure. But Pennsylvania species can be used. There's no technical reason why they can't be. You can specify them and demand that they be used, and that will increase the treater's interest in providing that material to you. And certainly this provides an opportunity for some of the low-value hardwoods in order to enhance Pennsylvania's forest resource potential. Again, if you were to build a bridge today or some other structure, the softwoods are those which are readily available, but the abundant supply of hardwoods gives you an excellent future in Pennsulvania for requiring use of this particular product. Thank you.